Hello, everyone. My name is Moiz Arif, and I am a fourth-year PhD student at the Rochester Institute of Technology. Today, I will be presenting our research on exploiting CXL-based memory for distributed deep learning. This work was done in collaboration with Micron Technology. In this research, we leverage latest advancements in memory subsystem to provide additional memory and fast scratch space to deep learning workloads to reduce their overall training time while enabling them to efficiently train models using data that is much larger than the installed system memory. First, I would like to discuss some key challenges with the modern data centers. These data centers consist of tens of thousands of servers, which are divided into clusters depending on the resource specifications. This introduces heterogeneity and results in varying resource profiles that cause the application performance to vary depending on the allocated resources. Similarly, memory and storage subsystems have varying throughput, IOPS, and latency, which also results in unpredictable application performance. Modern high-performance computing workloads, such as deep learning, require large memory, high throughput, and low latency I/O to train models with huge datasets. To summarize, the advancements in hardware technologies and complex resource requirements of these modern applications drive heterogeneity in modern data centers. In deep learning, we train models that typically consists of several layers over large data sets and require tens of thousands of gigabytes of memory. Similarly, limited memory availability on data center servers cause excessive swapping of data to the underlying storage, which cannot cope up with the ever-increasing I/O demands of deep learning workloads. This results in increased training time as the I/O operations can take up to 85% of the total time. To solve this problem, system memory of a server is expanded by installing high-capacity memory modules on all slots, which is expensive and accounts for about 50% of the total setup costs. To summarize, the data center servers should have enough memory to host the entire deep learning model and training data to maximize performance. To improve the performance of deep learning platforms such as TensorFlow and PyTorch offer multiple APIs and methods such as data caching and prefetching to create highly optimized data pipelines. A batch of data can either be cached in memory or in storage after it has been processed. However, for very large data sets, the entire dataset cannot be cached into the memory due to the limited memory availability. Similarly, the prefetching reduces the I/O stalls by loading the next batch into the memory. However, it too becomes ineffective for large datasets and with slow storage tiers. These built-in methods and APIs do not incorporate different memory and storage tiers for storing large datasets. Therefore, it is very important to have an intelligent data staging strategy that incorporates heterogeneity and multiple memory and storage tiers. We conducted several experiments to understand the impact of limited resources on deep learning performance. To capture the impact of memory bandwidth and latency, we ran stream triad benchmark using near and far memory. We observed that up to 70% performance there is a 70% performance variation when memory is accessed from near memory, which has a much lower latency as compared to the far memory, which has a much higher latency. Similarly, to capture the impact of limited system memory on deep learning performance with the MobileNet model and ImageNet dataset, we observed that as over time, the memory footprint of DL workload increases over time. And as we reduce the available memory from, let's say, 90% to 10%, the training time increases by up to 23% due to excessive swapping of data. So deep learning workloads suffer from performance degradation due to limited memory availability and data swapping to lower storage tiers. Another important aspect to consider is the latest advancements in memory and storage subsystems have offered improved bandwidth and capacity, such as Compute Express Link, Gen Z, and persistent memory. Talking specifically about CXL, it is a new cache-coherent interconnect for processors and accelerators over the PCI interface, and it can be used in a variety of configurations depending on use cases such as memory caching, pooling, and certain expansion scenarios. However, it is unclear how these new technologies, such as CXL, can benefit platform and applications. Now we will go over some key contributions of our research. We investigate the impact of resource limitations on the performance of distributed deep learning in heterogeneous data center environments. We also utilize latest technologies to optimize the performance of deep learning workloads by providing additional memory and fast scratch space. We develop proactive data prefetching, staging, and caching mechanisms to ensure deterministic performance of deep learning workloads. Lastly, we also develop and integrate the proposed framework with TensorFlow to reduce read and write latencies, training time, and improve the overall I/O throughput. Now let's go over the architecture of DeepMemoryDL. On the top layer, we have our deep learning workloads that are running on the distributed TensorFlow environment, and the deep learning framework is tightly integrated with TensorFlow, and the boxes in green are our contributions. On the TensorFlow master node, we have the core module, workload analyzer, resource gatherer, prefetcher, and the manager module. While the worker node reside closely with the TensorFlow workers, and they also have a prefetcher on them as well. The key responsibilities of the workload analyzer module is to analyze the workload and to capture model-specific information and any data optimization mechanisms used. It also divides the overall execution into data processing and model training phases. It is also responsible for analyzing the dataset and tracking data shards allocated to all the workers. And based on this information, it estimates the memory and storage allocations on all the worker nodes. Similarly, it also estimates the time required for completing the prefetching schedule on the memory and storage tiers. The resource gatherer, on the other hand, maintains the hardware specifications along with the current rated resource utilization on all the workers. And based on this information, it runs micro benchmarks to capture the performance statistics of each device, such as the total bandwidth, IOPS, and read-write latency. This information is also used to categorize these devices into tiers. And the core module is the central component of DeepMemoryDL and orchestrates various workflows of DeepMemoryDL. It uses information from the resource gatherer and the workload analyzer to identify prefetching and caching buffer sizes. These buffers are kept dynamic, and it depends on the batch size and the current memory utilization on each tier. The batches to be prefetched and cached are scheduled such that they do not exceed the allocated buffer space on each tier. There are two additional components of the core module. One is called the manager, which resides with the TensorFlow master and supervises all operations on the master node. It shares the batching schedule for all tiers to the worker nodes along with metadata containing the location of the input data. It also instructs the worker nodes when to start prefetching onto the tiers based on the information from resource gatherer module. The workers, on the other hand, are part of TensorFlow worker nodes, and they execute instructions from the manager, including monitoring of local buffers, caching, and prefetching data. The core module is also responsible for exposing CXL-based memory to the deep learning workloads and allowing them to use CXL memory instead of slower swap storage. And also it provides an fast alternative to store process data. The allocation is done in chunks of 512 megabytes. Similarly, it also creates CXL-based scratch storage space for workloads to use and read data from instead of from the slower disk-based storages. This is beneficial for prefetching and caching huge data sets where the available memory is not enough to store the entire data set, and it improves the overall pipeline performance as well. The main purpose of our proactive prefetching is that it prefetches data batches into the memory before processing or before each iterations in order to minimize the I/O wait. Prefetching works alongside caching policies to ensure that the data does not exceed the buffers, and it also helps perform data eviction when required. The prefetching schedule follows a set of rules that define the priority for data placement, which starts with the main memory, followed by the CXL memory, CXL storage, and then the available system storage. Similarly, as the data batches are read and they are cached in the reverse order until they end up in the lowest tier. To better understand this, the data set usually resides in the network attached storage, from where it is prefetched into the CXL storage, followed by the CXL memory. And once it has to be loaded into the main memory, it is done from the CXL memory, where the batches are read. And after they are done processing, they are prefetched into the CXL memory, followed by the CXL storage, and eventually they end up in the SSD-based storage. And if the data batch is required again, it is read from this SSD-based storage into the CXL storage. Now, the Prefetcher module executes the prefetching schedule as defined by the core module on all the worker nodes involved in the training process. It also tracks the memory footprint of each sample, the size and the size of each training batch, and the buffers themselves to help keep the buffer size dynamic. The timing is very crucial to the prefetching process, and it launches the prefetching threads based on the latency and the data to be prefetched on each tier. So once the deep learning workload is submitted, it is the core module who gathers all the information from the resource gatherer and the workload analyzer to come up with a prefetching schedule that is shared with the prefetcher. The prefetcher then in turn executes the schedule on manager as well as on all the worker nodes. And once substantial data has been prefetched, the deep learning workload information is sent to the manager, and then it executes them in return. Now, the caching policies govern the overall caching process for all the deep learning workloads, and it ensures that the cache data does not exceed the buffer size on each tier. And it follows a first in, first out schedule, and the data is always cached from a faster tier to a slower tier. Similarly, in the event of an eviction, data is again evicted in the FIFO order, and in case the batch to be evicted is marked for prefetching, it is cached to a lower tier instead of being evicted entirely. So once there is a buffer full event that is detected on any tier, the event is carefully analyzed with the tier information and the cache buffer information. It is then further looked at in the prefetching schedule to figure out if the batch is needed in the near future or not. If the batch is required, it is then cached to a lower tier but if not, the batch is affected. We now go over the evaluation of our proposed framework, DeepMemoryDL. For the evaluation purposes, we used 8 servers with Intel processors, each with 192 gigs of memory and a 10G network interconnect. Half of the memory is reserved for emulating CXL devices or the FAR memory, and the CXL storage device is emulated as a RAM disk. We use distributed TensorFlow on Ubuntu 20.04, and to categorize each device into a tier, we run micro benchmarks such as stress, stream, ECM, and systat tools to capture the statistics. Similarly, we used ResNet, Inception, and MobileNet models with ImageNet dataset as representative workloads. To mimic a real-world limited memory availability scenario on each server, we developed and used our memory hogging utility. To evaluate various CXL use cases and how each configuration would impact the deep learning performance, we defined 6 unique execution environments. We start off by defining 2 baseline environments, which is the unconstrained environment in which there is no resource sharing between deep learning workloads, and followed by a constrained environment where the resources are being shared with all the workloads, and it results in a limited memory availability scenario. We defined 4 CXL-based environments, which are based out of the constrained baseline environment. In the CXL-based storage environment, we only have the CXL storage available to the deep learning workload. However, on the CXL-based memory environment, only CXL memory is available. Then we have a combination of both, where both CXL memory and CXL storage is available to the deep learning workload. Lastly, we have a DeepMemoryDL environment, which is based on the CXL-based memory and storage environment, but it contains our proposed optimizations. To evaluate the performance of our DeepMemoryDL, we reported the total execution time of deep learning workloads on these execution environments. We observed that DeepMemoryDL performed better as compared to other environments by up to 34%. We also observed that the CXL-based environments reported a slightly higher execution time as compared to the unconstrained environment, due to the additional latency associated with accessing CXL devices. Even though there is a slight increase, this allows the developer to solve a much larger working set size with an acceptable overhead. Lastly, the constrained baseline took the longest time and is represented by a more realistic execution scenario, and the CXL-based environments outperform the constrained environment for all experiments. So the observed performance improvement with DeepMemoryDL is attributed to the effective use of CXL-based resources and the implementation of prefetching and caching policies. Next, we evaluate the impact of the data preprocessing phase on the execution environment. We observed a performance improvement of up to 56% for DeepMemoryDL compared to the constrained baseline environment across all batch sizes. There is a heavy reliance on the underlying storage and memory tiers during this pre-processing phase. So when the data is loaded from the CXL-based storage, it contributes to an additional 20% performance improvement compared to a pure CXL-based memory environment. Lastly, the effective use of CXL-based memory and storage with our data staging optimization resulted in the lowest processing time. Next, we also wanted to capture the impact of CXL-based memory allocations to the deep learning workload given a batch size of 64. We observed that as the workload uses more and more CXL memory in lieu of the slower swap storage, the execution time continues to decrease. So smaller CXL memory allocation resulted in excessive swapping to storage, which in turn resulted in an increased execution time for the given deep learning workload. We further investigated the impact of CXL memory allocations on deep learning workload by varying the batch size from 64 to 512. Our evaluation showed that the lowest execution time is when we have the maximum allocation to the deep learning workload. And as the allocation decreases, the execution time increases proportionally. And the execution time continues to increase as we increase the batch size as well. So DeepMemoryDL adjusts the buffer sizes to cater for the change in prefetching and caching policies due to an increased footprint of each batch. We also conducted experiments to evaluate the impact of using CXL-based storage for data staging purposes. We observed a performance improvement of up to 32% compared to the constrained baseline environment. Similarly, the performance improvement of DeepMemoryDL is due to the reading of input data from CXL-backed storage, which has a much higher read bandwidth than IOPS. Similarly, we evaluated the impact of our data prefetching and caching mechanisms on deep learning performance. We observed a 10% increase in the execution time when comparing unconstrained environment with the CXL-based memory environment. Similarly, the execution time decreased by up to 17% when comparing constrained baseline to the CXL-based memory environment. The DeepMemoryDL prefetching and caching policies resulted in the performance improvement of up to 30% compared to the constrained baseline environment. Lastly, we conducted performance scalability testing of DeepMemoryDL to evaluate its performance at scale. And we observed that our framework outperforms constrained baseline environment in all experiments, and the differences remain fairly consistent as the number of workers increase in a distributed setting. This shows a negligible overhead of using our framework with increased worker nodes. In the end, I would like to summarize our main points of our research. We observed that the resource requirements of modern deep learning workloads typically exceed the available hardware resources. Similarly, popular deep learning platforms do not incorporate varying performance profiles of memory and storage subsystems. We propose a framework called DeepMemoryDL that improves the performance of deep learning workloads by proactively prefetching and caching data into CXL-based devices. Overall, DeepMemoryDL reduces the training time by up to 34% and 27% as compared to the default TensorFlow and CXL-based memory expansion scenarios, respectively. In the end, I would like to thank everyone for their time and listening to our presentation. If you have any additional questions, please feel free to reach out to us. Thank you.